So again, welcome you back to our final session for the inverter fundamental and grid support tutorial. So this session will try to give you an overview of what has changed in the IEEE 1547 2018 version, some of the major changes, and also talk about briefly that how products are going to be certified using the UL listings. So those will be the main topics here. Again, we are recording this webinar. This is the final topic. So first, I would like to highlight those of you who are familiar with the 1547 standard. The previous version was most probably 20 pages was the main content. 2018 is 200 pages. So you can easily imagine that in an hour or 2 hour long course, it's not possible to go all the details. So I'll be covering mostly the major changes in this standard. And just because of IEEE, these are my opinion, not IEEE opinions or interpretation. Some disclaimer. So this is the standard I'm talking about. If you're not familiar with, it's a DER interconnection standard applicable for any distributed energy resources connected on the distribution system. So it does not differentiate by voltage. It uses the term that if it's a distribution connected, then this standard will be applied. And I think it clearly says that this standard is not meant for transmission connected system. And you might be familiar that there is a standard ongoing, standard development ongoing, known as IEEE P2800, which is still in the development stage. Most likely target is to publish next year. That is intended for transmission connected IBR system, inverter-based resources. So just wanted to highlight this standard. By official language, it is applicable for distribution connected system. It was approved in 2018, but actual work took place between 2015 and 2017, over 3 years. A lot of work. There is an amendment published this year for this standard. So you are supposed to use the standard including the amendment. If you only look into the 2018 version, you will miss a change that was made in April or June of this year. And for some reason, IEEE published them as a separate document. So you have to have both documents to see what was changed in the 2020 amendment. What is the number for the transmission connected inverter standard again? I'll type it. It's IEEE P2800. So P stands for is still in the development, so it's not complete yet. So IEEE P2800. So again, I'll talk about what is being changed in the amendment, but I just wanted to make sure you know about this amendment. And then there is another standard, which is the test standard. So remember, 1547 is the root document. It only specifies what are the requirements, performance requirements. Then .1 explain how to verify those requirements, like what test you have to run, how you run the test to verify those performance for either the inverter or the DR level. So that's the relationship between 1547 and .1. So .1 is the test standard, and 1547 is the root document. So if I quickly go through the timeline, the first version was published in 2003. Again, it was a 4 or 5 years of effort. Many of our senior EPRI folks are involved in that time. Like many of you know Tom Key, he was also involved in that one. That time the mindset was anything happened, the DR should disconnect. The system will recover, like utility will bring the system back, and then DR will come back after 5 minutes. So the whole mindset was shall not actively regulate voltage. Clearly says the shall not. Shall trip on any abnormal voltage and frequency conditions. So that was the mindset of 2003. By that time, 2013, 12, 13, because of high penetration in Hawaii, high penetration in California, high penetration in Germany, there was a thought process that not involving those resources into any sort of grid support is not a good idea. But any modification will take a couple of years. That's why there's an amendment done in 2014, which basically remove those sentences which where it says shall not and replace them with a may condition that may actively regulate voltage, may write through, but it just removed the barrier but did not specify anything specific that what it has to do. So that's why it kind of it depends on between the utility and the vendor what they want to do. That is still okay because that allowed the California Rule 21 Phase 1 functions to be implemented. Several utilities did pilot projects with some level of smart inverter functions. So those were the period was in that. But immediately after finishing the amendment, the actual revision of the standard started 2014-15 timeframe, and that resulted into publication of the full revision in 2018 March-April timeframe. And this time the language is totally reversed. Shall be capable, it's not that they have to do it, but has to be the capable of actively regulating voltage, shall write through abnormal voltage. So in the standard, shall means you have to do it. May is that may or may not do it. So that's why shall is very important. And same thing, frequency response. So you can clearly see the transition from doing nothing to the opposite direction that have to be capable of doing it. And I already mentioned that this is not for the transmission connected system. And the third bullet, I should have removed this draft watermark. It's no longer draft. This third bullet is important. It specifies capabilities and functions and not utilization of these functionalities. Utilization is still up to the utilities. The distribution system operators at that particular location will decide which function to be active, whether any function will be active or not, which setting will be used. So that decision is still up to the distribution system operator or utilities. But what the standard says that if the product has to be certified, say 1547-2000 certified, then certain capabilities and functionalities has to be available for utilization. So capabilities and functions are mandatory, but not the utilization. So if you are not totally familiar, this may be a big topic to understand in a short time. The couple of points. IEEE standards are technology agnostic. So basically it says you cannot say this requirement is for inverter-based resources. This requirement is for synchronous generator. It does not allow you to discriminate based on the technology. But at the same time, we realize what the power electronics based DER can do may not be feasible, at least economically feasible by rotating machines. So after a lot of discussion, the working groups kind of come up with the idea that let's define the requirements as a performance categories. And for example, for the write-through requirement, the performance are defined into 3 categories, category 1, 2, 3. Category 1 is the minimum requirement in terms of how aggressive low voltage condition has to be stay connected, whether category 3 is the most aggressive one or more deepest voltage and longest time it has to stay connected, which is more challenging. So that's how it's being defined, that from relatively easy to the more severe requirements. Similarly, for the voltage regulation section, which I led, we defined the requirement in 2 categories, and we'll explain that what does that mean. So idea is that now by having this flexibility, now vendors have option, depending on their technology, depending on which market they want to go, they can get their product certified, for example, category 2 and category A, or they can do category 3 and category B, highest performance categories. So that gives them the flexibility based on technology, the cost, and the market they are targeting. Similarly for the utilities, which here is called authorities governing interconnection requirements, that complex. Basically, whoever has the authority to make the decision, they will also decide for a certain location, certain substation, or certain area, what performance category is required for DER. And utilities can decide that, okay, for inverter-based or smaller system, I'll ask for category A and category 2. For larger plant, I may ask for category B and category 3. So it also gives flexibility to the utilities or the authorities governing interconnection requirements to what performance category you ask for certain type, certain size, certain technology. You can ask for defined performance requirements. So it kind of gives flexibility of both stakeholders and also gives the flexibility that you may not have to always enforce the highest category for everything if that's not required. And we'll briefly talk about what is the differences between those categories. But any question? This is an important topic if you are not already familiar with this. Okay, hearing none. There are several topics like that, so maybe we'll not get time to do everything. The other point that I mentioned before, and I think one of the question was there, RPA, the reference point of applicability. In the new standard, there are a lot of requirements like write-through, bold var, power factor, which depends which location you are asking it to implement that. So it was not like the older standard that you respond to the frequency and voltage, and they're pretty much same. Not much dependency. So here, there are two main concepts, PCC and POC. POC is simple. It's basically the terminal of the device. For example, inverter's terminal is known as POC, point of connection, where it's connected electrically to the system. PCC is a little bit complex. Depending on which type of facility, is it just a load, just a generation facility, or mixed with load and other equipment. So that's an example that if it's a pure generation source, like the one that is shown in EPS2. So I'm not sure you're seeing my cursor. I'm trying to show it here, the EPS2. In this case, there is no load, nothing there. So the POC and PCC might be a difference is there is a transformer in between, a couple of transformers in between, as is shown before in the first session. But these are almost electrically same point. And this type of facility, the requirement will be applied at PCC because it's a pure generation source, especially if it's larger than 500 kW. On the other hand, if it's a mixed source like a load, a DER, a PV facility, or energy storage or hybrid system, and then some supplemental device like cap banks, or even a STATCOM, some mix of resources, or a plant controller. So those cases, this will be considered as a POC where the energy DER and the supplemental device are connected to a location, but PCC will be the combined system where it hands over from customer to the utility. So that will be the PCC. So the question is, where is the RPA? So in the standard, there are two actually flow diagrams or a flow chart. It shows the conditions. So I'll not go through the detail, but very briefly, if it's a smaller system, especially less than 500 kW, the reference point of applicability will be the POC. So basically, the DER terminal is where the requirements will be applied. So you can think about all the residential rooftop system, all the small commercial rooftop system below 500 kW. For those, all these requirements will be applied at the terminal of the DER. Mostly, you can think about inverter, but DER is combination of whatever goes behind it, inverter, plant controller, modules, everything. So that's where the rules applied. On the other hand, if it's a larger facility, larger than 500 kW, even if there's a load is less than 10%, or it's just a pure generation source, so 1 megawatt, 2 megawatt, solar garden. So many of you have those type of facilities, 1 megawatt, 2 megawatt, pure generation facilities. For those kind of things, the requirement will be the PCC, which is most cases the metering point where it hands over from customer to the grid. So those are very nutshell, that higher level differences, but there are a few more details are in this standard. So once you identify the RPA for a site, then all the standard requirements are being applied to that RPA point. Any question? Most probably you guys are tired, but let's hang in there. We'll finish it quickly. Then what is the difference between from voltage regulation or reactive power capability point of view, category A and category B? So remember that in voltage side or reactive power control and voltage regulation support function point of view, there are two categories, A and B. Let's explain the B first, and then it will be easier to understand A. So B is saying that the DER has to have a certain reactive power capability available. Whether it's used or not, that's a different question. Capability has to be available all the time. What it is actually, if you see this right bottom figure, that from 20% to the P rated power, from 20% to 100%, it has to have 44% of the VA capability available as a reactive power capability. So it's not a triangular, it's a square wave requirement, square shape. From 20% to 100%, 44% of the VA limit has to be available anytime the system needs it. And another slide I'll explain a little bit more details. Below 20%, but above 5%. So between 5 and 20%, there's a slope. The requirement gradually reduces because of difficulty to maintain the amount of reactive power. So that's how the standard, and it's symmetric on the injection side and absorption side. So that's the category B, reactive power capability. If you go to the reactive category A, positive side is same, injection side is the same requirement, but in the absorption side, the requirement is reduced to 25%. I forgot the explanation, but it was for some rotating machines, it was difficult to maintain high reactive power without a more rotator current or something like that. And that's why there's a compromise that let's reduce the reactive power absorption requirement for category A. So we're not saying that which one is inverter, which is a rotating machine, but there's a room for rotating machine to get certified also. So that was the kind of the idea. So if you notice the note in the bottom, which category you want, that's a utility decision that, again, as I mentioned, depending on the technology, depending on the size, depending on the location, you can take a decision that certain cases you ask for category A performance, certain cases you can say, I need category B performance. So that's up to the utility to decide. So I'll explain that requirement a little bit more details using the category B example. So as I mentioned before, this red area is the must required capability, or to say that other way, minimum required capability for category B DR. So if any DR has to be certified for category B, they has to have this reactive power capability as a minimum requirement. So again, all the requirements are minimum. There is no upper limit. It can go all the way to circle as a minimum, no problem, but it cannot be less than that. Now, what happens? This area, this semi circle type area. So before that, again, I just wanted to know, many of you are used to define reactive power requirement as a power factor, but this is not a fixed power factor. For example, if you see at P rated, power factor is equivalent to 0.9, but at 20% power level is equivalent to power factor of 0.378. So power factor is changing, but reactive power is a constant requirement between 20% to rated 100%, and then there's a slope below 20%. The other part, the hatch part on the blue part on the right, which is the inverter can or DR can operate there, which is more real power generation, but if there's a reactive power needs, they have to immediately reduce the real power and provide the reactive power support needed. So they cannot say that, oh, I'm operating at this point and I cannot give you the reactive power. That will not be allowed. So before I go there, so if it's operating somewhere here and there's a volt bar or power factor needs this much reactive power, then it has to immediately reduce the power and go there. So that's what is being added, that, okay, you can go there, as long as you come back and give me the reactive power when needed. So far that's what is minimum requirement, what is allowed. Then what happened to the rest of the white area, which includes entire left half, which represents power absorption from the grid, which is equivalent to charging the battery, right? Or between 0 and 5%, which is equivalent to nighttime. So what happens to nighttime when there is no solar or solar generation is less than 5%? So these are not the minimum requirement. So by standard, nobody can say that DER has to provide that because the standard says so. But it's also not prohibited. Operation in this zone is not prohibited, but not included as minimum requirement. So that's the point I wanted to highlight here. The red area is minimum requirement. Blue area, you are allowed to go there. The green area is not prohibited, but also not minimum requirement. So if you ask for reactive power support during night time, or energy storage when charging has to provide volt-var function, then that may have to be some sort of a agreement, or your EODR interconnection requirement has to specify that. 1547 automatically does not guarantee that. Important topic, if any question or need more clarification. And actually in our program 174, we published a white paper explaining those type of details. Okay, so if there's no question, so that was, okay, there's a question, VAR at night, does it require any hardware modification? Good question. Couple of things I can think about. First of all, if it's a retrofit scenario that there is a system already in the field, now because of the need, the manufacturer will retrofit it to enable the nighttime. That time a major question may ask me how old the existing hardware is. If the hardware is relatively new, most probably those capabilities or VAR support capabilities and few other things are already being available. So in that case, one major change can happen that I can think of, like if the control electronics of the inverter is designed to get powered from the DC side, like the early morning panel will start generating DC power, and that will power the control electronics, which will do all the switching, monitoring, everything, then that will not work during nighttime. So if that's the scenario, then the modification will be something significant. Either they have to put UPS or they have to put some rectifier to get the power from the grid, control electronics power I'm talking about, to keep the electronics running so that the plant can generate power. If the inverter was already powered from the AC side, then might be a little bit easier in that case that, okay, I still have power available nighttime to keep my electronics running. In that case, it might be some software changes in the system. Recently, we are doing a project, again, the same example that I gave before, is a transmission connected system for nighttime reactive power support. We didn't work directly with the inverter manufacturer, so we don't know the exact story. But what we are seeing is that for that particular plant, which is not their latest model, the inverter has to go to the sleep mode during the in the evening, and then come back again in the nighttime mode. So there has to be a transition of the mode between normal daytime mode and the nighttime mode, which should not be the case if it was designed for that from the get-go. And I think the argument was some requirement in the National Electric Code of 2014 prohibits them from keeping running. So I don't know the details because we didn't work directly with the manufacturer. We are working with the system integrators, and a lot of information gets lost when you go a couple of layers of communication gaps. So that particular plant worked nighttime, but it goes to the sleep mode after 15-minute comebacks into nighttime mode and then continue operation. But my suggestion is that if you have any project where you want to do it from the RFP stage, make it very clear that you want the nighttime reactive power support. And most major manufacturers should be able to support that at this time. Long answer, but I hope I answered your question. Okay, so after we go to the reactive power capability, that's just what type of reactive power capability you have to have. Next question is what functions I have to have, control functions I have to be available. Again, these are the capabilities, function capabilities has to be available, not necessarily means they have to be activated. Activation decision is still the utilities will take the decision. And if you see the difference between category A and category B, clearly you notice category B has all the functions required. On the other hand, category has two of them not required or not mandatory. One of them is watt var, we'll discuss that soon, a couple of slides. And also the volt watt is not required for category A. So that's how the categories are differentiated. Little bit of less reactive power requirement, two of the functions, control functions that are not required. So that's how the difference between category A and category B. And I used that example before. This is basically a bunch of functionalities. Use of that function is up to the user. Now, how each of those functions are defined. So I'll not show you the exact table, but I'm giving an idea that how they are being defined in the standard. For each of those control functions, you'll see this figure is most probably in the appendix, not in the actual section. You have to flip through the appendix section. But ultimately, as I mentioned before, it's defined as a 4 pair of points, V1, Q1 through V4, Q4, and Vref. And in the table, which is in the main section, you will find two categories of information. First is the default settings, and then another one is the range of allowed settings. So what does that mean? So if I pick the category A, if you go vertically, it defines all the parameters that you need to define a Volver curve, and it gives the parameter values which should be considered as a default value for category A. Similarly, it gives all the parameter values that you need for category B, and if you want to use those values, you can just say category B default settings. Then automatically this column will be activated or will be selected. However, if you feel like that, oh, I have a severe program in this region, so I don't want VREF to be neutral. I want them to be 0.98. Or this system is very close to the substation where voltage is always high, so I don't want its reference voltage to be 1. I want its reference voltage to be 1.02, so that it doesn't always has to produce reactive power or absorb reactive power. So if you feel like those type of custom arrangement you have to do, or this is a 4 megawatt, 5 megawatt plant, which you want to do more specific setting for certain applications. So then you have the flexibility to change those default values within a range. And for each of those parameters, there's a range specified. For example, VREF default is binominal, but can be anything between 0.95 to 1.05. So what is the importance of this range of adjustability? If, as a utility, you want to decide to change the VREF from default to any value within that range, the product doesn't have to be certified again. There doesn't have to be any mutual agreement between utility and the system operator, DR operator, because these are already allowed by this standard. So as long as your requirements say that you want IEEE 1547-2018, automatically default and the adjustable range become available to you. And product certification will cover both the default settings and the adjustable range. So there will be no need for new certification for those products. So those are the most two important things to remember. Now, is it possible to have a setting outside that range? For example, whatever reason, if you want to use 0.93 as your VREF point, the standard does not reject that. The standard doesn't say that you cannot do that, but it's not automatically also approved or included in the standard. If you want to use anything outside the range, then that will be a mutual agreement between the utility and the DR owner or operator. So the way the standard is written, nothing is prohibited, but certain things are automatically approved and no additional approval or coordination agreement is needed for the utility to use them. But outside that, any new function, any new parameter outside the range, there is no restriction, but there is a mutual agreement required. So there is a sentence somewhere in the standard. Any functions outside, other than which are specified here, are also allowed with mutual agreement between the EPS operator and the utility and the DR operator. Any question? So I'm not showing the entire table because I'm not supposed to copy the entire IEEE standard, but you can get an idea that for all these 4 pair of points, VREF, and the open loop response time is specified in the open loop response time. And the open loop response time is actually, forget this number, for category B, the default is 5 seconds. And the fastest can be 1 second and the slowest can be 90 seconds. So I said half a second, but that's not correct. For category B, the response time is default 5 seconds. Minimum can be 1 second, maximum could be 90 seconds. So this is another function we did not discuss in the previous session. One main reason is this is a relatively new function or new control function being introduced into the 1547-2018 version. And so far, we haven't tested any product that offered this function, but things will change, of course, next year or year after when more products come into the market. So this is basically a kind of fixed reactive power mode, but the difference is here, you allow this, just think about the right side first, then we'll go to the left part. If you, where's my laser pointer? Okay, what happened? Okay, so if I can see my, I hope there's a pointer, okay. So up to this range, up to this power generation level, so from 0 up to say 40%, 50%, there is no need to provide any reactive power support. So that's the idea here, that you are not causing any voltage problem, so I don't need any reactive power from the DR. Above that level, if you remember our first example that I showed in the morning, above 50%, that plant was causing over voltage. So those type of scenarios, the more power you generate, more voltage goes high. So you need more reactive power to push the voltage down. So that's the definition here, that you do more reactive power when you cause more problem, which is kind of a higher generation, push the voltage higher, so you need more reactive power to push the voltage down. So that's the idea, rather than having a constant bar all the time. So that's what this function means, and this is a reactive power. There's another function known as watt power factor, which was in the German grid code, but we decided not to include that in the 1547. In that case, this will be power factor rather than bars. So y-axis will be power factor, x-axis exactly the same, and same idea, that up to certain power factor will be unity, and then you will have an absorbing power factor. And there's a reason for doing that. Power factor will have a non-linear reactive power, so there can be a sudden change in the reactive power. So we wanted to have reactive power more like 0 and then linearly changing. So that's why the group decided to use watt var rather than watt power factor. After that, the same idea is the default settings are defined, then adjustable range are defined for all the parameters. So this idea is the same. So one additional thing you can think about, what is this means? So entire left side is only applicable if the DER can absorb power. So that's the language used in the standards. So you can understand that PV cannot absorb power. So this left side will not be applicable for PV. So this is mostly applicable for energy storage when it's in the charging mode. Function is defined, but if you remember my previous comment, when it's a charging, minimum reactive power capability is not a minimum requirement. So storage may not provide that also, since there is no minimum requirement when it's charging. But if it offers that function, then that can be useful, that when you are absorbing power, most probably will cause low voltage. So at certain point, you may have to inject VAR to push the voltage high. So that's the idea here. It's opposite of excess generation causing over voltage. So excess load will cause under voltage, and you need some support. Any question? Okay, if not, if I can move to the next slide. Volt watt we discussed before, so it's the same function. And again, you can see it's a P rated. And from there you go down. P1 is the threshold. Those are defined here. Only additional thing you can think about what is happening here. For PV, this figure will be applicable because PV will be generation. There is nothing called absorption for PV. But if it's energy storage, if this side is the generation, the opposite is the absorption. So basically, energy storage can start reducing its discharge, reducing the discharge, going all the way to 0 discharge. If the voltage still continue to go high, which means excess generation, they can start charging to help regulate the voltage. So that's the idea here, that if it's energy storage, which was discharging with high voltage, they can start reducing discharge, which will be effectively reducing the generation, go all the way to 0. If the voltage still continue, if they have room to charge, they can go in the charging mode to increase the load. So that's how it's been defined. Whether products will offer that or not, that's still to be, we have to see it. Any question? Okay. So those were voltage related two categories, category A and category B. when it goes to abnormal operating condition, abnormal voltage and frequency condition, there are three categories. Category 1, 2, 3. I'll show some figures later, but basic idea is that category A1 has the minimum requirement in terms of how severe voltage it has to ride through. On the other hand, category 3 is the most severe low voltage and longer period fault it has to ride through. I'm not showing you the exact diagram, showing a concept diagram. If you guys have access to the report, you can definitely see it in the appendix section. So if you compare category 1 and 2, clearly see a couple of same areas you see shell trip, both has continuous operation from 88% to 110%, they're all same. Mandatory operation in category 1, mandatory operation category 2, permissive operation. So what is you see main difference if you pay attention, you can see this mandatory operation depth is more deeper than this one, and it's longer than this one. So this just means that category 2 has to stay connected for the lower voltage for longer period because its ride through region is wider and deeper than category 1. So that's kind of the main difference, that higher category, the DR has to have more capability to ride through more deeper and severe voltage and condition. So this is what I wanted to highlight in the morning in the previous section. Category 3 is a little bit more challenging. It goes all the way to 0 voltage for certain time, but it differentiates up to 45%, if I'm not mistaken. It has to be mandatory operation, inject current to the system, most probably reactive current to the system. There are more details in the standard. But if it falls below that, say most probably 45 to all the way to 0 for certain time, like this part, it has to stay connected, but don't have to inject any current. And once the voltage recovers, it has to come back quickly. So it will not go through the 5-minute waiting period and then resynchronization period because it's still connected. It just stops switching the gate. If you remember the first, second session that we had, everything is by switching the gate. So if you stop switching the gate, there's no current flow from the DC side to the AC side. So that's what it will be doing in this time, that stop switching, no current injection, but you'll keep the contactor closed and it will come back immediately if the voltage recovers. So the idea was that for a transmission level fault for a few cycles, if the voltage go further low, you don't want the system to shut down. You want them to come back immediately after the fault is recovered. And there are some detailed description of what does momentary cessation means in terms of definition. I mentioned that it doesn't have to inject any current. However, if you remember, inverter in its output stage has filter, like LC filter. So since you are not opening your contactor, the filter may still exchange some reactive power with the grid. So that is allowed. So if you don't see a 0 current, that doesn't mean that it's a failing. It might be only exchanging reactive current with the grid because of its filter connection. Two details, but I'm just trying to highlight the main points. And this is the example I wanted to show before. I already showed that example of a momentary cessation. So voltage went all the way to 0 for certain time. The result of that, inverter stopped switching, no current, maybe some slight reactive current. Once the voltage recovered, it took some time, but not necessarily more than 0.2 seconds, and then came back to the normal operation. So this is what momentary cessation offered, that it can come back very quickly since it did not open the contactor and did not lose the synchronization. Any question? How fast does the inverter needs to come back after momentary cessation in general? That's a very good question. There's a number in the standard, but I don't remember that right now. EOA, if you can hear me, do you know the number by heart? After momentary cessation, how fast they have to come back?
I need to check. I don't know on top of my head.
Yeah, if you have the standard, take a look at it, and maybe when you find the numbers, let the group know.
Okay, I'll post it on chat.
Most probably there is a number, and there are some ramp rates also defined that after fault, after momentary cessation, you come back with a what ramp rate. think those are specified, and that's why it's a 200-page document, which was before 20-page only. So we'll try to find it, but I think it's in the standard specified, that the recovery rate. This is another study just showing that it was done by most recently by ISO New England. Same thing is showing that if there is a fault on the 340 kV system line, this entire blue area will see a suppressed voltage. So this voltage will be lowered because of the fault, and resultant of, if you don't have write-through capability, then all the DR connected in those areas will be disconnected, which was not a problem before when we have a few systems and aggregate impact was not large. But now, because of the high penetration at certain locations, like Mass is a location with a lot of solar, they cannot afford to lose that much of generation for a transmission levels, very common faults. So again, just the same argument, why write-through is required. So one question we frequently hear, commentary here, mass disconnect is an adjustable parameter. You can move the threshold, that as you mentioned, that we sometimes extend the trip settings to see how the inverter behaves during fault condition. So trip settings is an adjustable parameter. However, write-through is not a configurable or adjustable parameter. It's a design parameter. So what does that mean? So we are asking the inverter or DR to stay connected for a voltage as low as 45% for 20 cycles. If it's all the hardware is not designed to survive that, like this voltage regulator, its contactor, if they are not designed for that low voltage for that long period through some UPS or some other mechanism, then they cannot stay connected. Their contactor will open, their regulator will drop off, and their control electronics will lose power. So that's why write-through is a design requirement. It has to be designed for that level of low voltage, that long period. If it's not, then by software change, you cannot activate that. And that's why the idea is that if you want less write-through capability, you select category 1. You want more write-through capability, you select category 3. But once you select category 1, you cannot ask it to do category 3 write-through anymore, because it's not designed for that. Similarly, if you have a write-through category of 3, inverter will not have any adjustable parameter, at least user adjustable parameter that can make it a category 1. So that's the idea, that if it's designed for that, that will be available. Now that created some, I think, challenge or issues with some distribution protection engineers who did not like this very long write-through capability of category 3. But on the other hand, bulk power system, transmission system people, considering the future of high penetration, they wanted to have the most or highest write-through capability available, which is category 3. And long story short, maybe some of you can highlight, there was some practice that, okay, if I cannot shut down the inverter, I'll put a relay in front of the plant, and I configured the relay to shut down for those voltages that I don't want to allow. Or I'll not use category 3 at all. So because of all those discussions on what happened between 2018 and 19, the working group decided to make some amendment in the standard, which is the 1547 Amendment 2020. That's I was talking about. There's an amendment published this year. What it does is basically allow, so what you are seeing in this figure is number 1, number 2. These are the corner of the mass disconnect. You can push those points or the settings all the way to this point. So what does that mean? Now this gray area will be extended all the way to here and then come down. So basically now any voltage which is below 50% and longer than 0.16 will fall into the gray area, which is shell trip. And effectively it will not write through this part, because priority-wise, shell trip is higher priority than master stay connected or momentary cessation. So in the 2018 version, overlap was not allowed. That trip setting was adjustable, but it cannot overlap the write-through requirement or momentary cessation requirement. So that's being now changed in the amendment. especially for category 3. I don't think there is any change in category 1 or 2. Only for category 3, it now allows these trip settings to be configured or adjusted, overlapping the write-through requirement. For example, 88% can now go all the way to 2 seconds, and 0.5 can go all the way to 1.16 seconds. And those of you who are familiar with the 2003 version, that was exactly what was there before in the 2003. Below 88%, within 2 seconds it has to disconnect. Below 50%, within 10 cycles it has to disconnect. So it effectively gives you the same disconnect requirement which was there before. Only thing it guarantees is now, when it's not disconnect area, it will be must write through. So that's kind of the difference here. So in a nutshell, that's the change that's being done. What does that mean? So let's do an exercise. So if X represents a fault, an event, which has 65% remaining voltage, so basically voltage dropped to 65% for 3 seconds, whether DR should trip or stay connected. Any answer? So answer is really depends. If I keep the trip settings the way it is right now shown, this like number 1, the 0.1, if it stays there, then this fault falls into the mandatory operating range. So that means it has to stay connected. So with default trip settings, which gives it answer will be right through. But if I move the number 1 to all the way to 2 seconds, and remember that this is 3 seconds, so that means now gray area extends up to this. In that case, the fault will be in the must trip setting or shall trip area. So in that case, it will be trip. So that's how this now, you can effectively adjust the trip settings to minimize the write-through requirement. And that's that expectation is that that will convince more people to take the category 3 right now, extend the trip settings so it will not write through longest duration. But 2 years, 5 years later, if you need more write-through, you can just change the trip settings and have more and more write-through allowed by the category 3. So as per my understanding, that is the rationale, that to motivate people to think about category 3 adoption more, even when if they don't use it right now, they can have the capability available, and later when needed, they can change the trip settings to have more write-through capability. So same thing if we think about why. With the default setting, this is in the momentary cessation part. So it should go into momentary cessation and come back immediately. But if I move the number 2 all the way to here, 0.16, then that will be in the shall trip area, and then it will trip. So that's kind of the way to interpret. Any question? And I saw that my colleague Iway also copied the section from the standard that talks about return to service. Any question regarding the amendment? So I'm trying to explain you 2 things I want to achieve, that you make you aware of the amendment and make you aware of that now trip settings can be adjusted to reduce the effective write-through in the category 3. Does 1547A also allow you to shift the blue points 1 and 2 down to 0? Yes, so 0 was, I think it was already there, if I'm not mistaken. Yeah, so you're absolutely right. I only talked about the time shift, that it can go from 11 seconds or 20 seconds, it can go 2 seconds, but at the same time, the magnitude can also go from 88%, looks like, all the way to 0%. Yes, you're absolutely right. I also don't know if you go that low, then there's no shall trip then anymore. That's confusing. Yeah, most probably not go all the way, but somewhere halfway. Yeah, exactly. That was my also thinking, that there'll be no shall trip anymore. Yeah, maybe I need to check it one more time. That sounds weird. Okay, and when it comes to frequency, there is no difference between category 1, 2, 3. So it's kind of the same argument. Frequency is a global parameter, so it doesn't matter which technology, where it is, the requirement should be same for everybody. And that's what you are saying, that there is no difference between category 1, 2, 3. So those are the major changes in terms of power, like what type of electrical behavior it has to do. Another major change in the standard is a requirement of a communication interface. So if you are relatively new to this area, in the 2003 standard was very clear about electrical interconnection between the DR unit and the area UPS, which is the basically distribution system, but there was no mention of communication. In the new standard, if you see this dotted line and the dot, it only indicates that DR has to have a communication capability available at its terminal, DR terminal. That's its responsibility. It's not responsibility to connect all the way to utility control center. That's not their responsibility, and you cannot ask for it. But you can say that the DR has to have a standard communication interface with one of the standard communication protocol available, so that you can connect with that system using your DOMS or your TMS or whatever mechanism or SCADA, whatever you want to do it. So that's also being added in the new standard. And if you remember the experience of Germany not having a communication, they had to roll out to 300,000 plus systems, connect laptop and change the firmware to activate that function. So that's kind of the lesson learned. So what it means, if this diagram, the left side, which is your utility communication network, basically managed or owned by the utility, that's not within the scope of this standard. Similarly, what goes inside the plant, like how in a 2 megawatt plant, a plant controller talks with 15 inverters behind the fence, is not covered by this standard. It could be RJ45, it could be Bluetooth, whatever the manufacturer or the system designer wants to use, that's also out of this scope. But what the scope says, at the edge of the DR, if it's just a rooftop inverter system, then the inverter terminal or inverter cabinet, or if it's a 5 megawatt plant with a bunch of inverters, plant controller, transformer, everything, then at the edge of the plant, basically plant controller or some sort of gateway, has to have this communication capability available. And what does that mean? It has to have one of those 3 communication protocols supported, 2030.5, also known as SCP2, IEEE 1815, also known as DNP3, or SunSpec Modbus. Those are the 3 standards kind of matured with the smart inverter functions because of the work done in last 10, 12 years. So that's why they are listed, because IEEE cannot pick one protocol, then that will be another problem. So it basically listed all that known protocols available that can support the smart inverter functions. So here has to support at least one of them, whether it supports more than one or it supports a proprietary protocol in addition to one of the standard protocols, those are no limitations there. The requirement is that it has to support at least one of those 3 protocols, and the transport layer and physical layers also have to be supported accordingly. So the whole idea is that even if as a utility you don't connect with the DER right now, maybe 5 years later, you'll roll out your communication network for your AMI system or some other system. At that time, you may also want to connect with at least the larger systems for primarily monitoring purpose, and then secondary also for control purpose. So at least DR will be available. You don't have to throw the DR out and put a new one, or you don't have to put a bunch of expensive communication interface later. So that's the idea here. Any question? Slide 25. Okay. On slide 25, for a close-in 3-phase fault on the BAS system, the voltage at PCC may see a dip to 0.65 per unit, as the line relays may take 3 or 4 cycles to clear the fault. Is this new proposal in the IEEE 1547 standard saying that the DR needs to trip? And understanding correctly. Okay, so looks like the fault that the DR will see at its terminal is 65% for 3 or 4 cycles. So let's go there. So where's my pointer? Okay. So 65% somewhere here for 3 cycles. and this is time. So 3 cycles will be what? Around 50 milliseconds. So 50 milliseconds will be where? This is 10 milliseconds. So it will be somewhere here, if I'm not mistaken. It's a log scale. Somewhere here is the fault. Now, if I see this curve and don't move any point, say the shell tree represented by the gray area, mandatory operation represented by the blue dot area, then this fault is in the mandatory operation range. So that means if you ask for category 3 requirement for that particular site, then it has to stay connected. Basically, it has to be mandatory operation, go through the mandatory operation part. So that's first answer. Of course, you have to have a category 3 requirement for this site and don't change any shell trip or anything. Now, even if you move this shell trip all the way to 2 seconds, you said the fault is for 65% for 3 or 4 cycles, which is way here, down here, compared to 2 seconds. So still it will be in the must stay connected section. So it actually not allowed to trip for that magnitude of voltage fault and duration. Once category 3 is right to requirement is make requirement for that. Okay, yeah, so maybe I didn't highlight also the time scale is in the second, not cycles. Good question. How resilient is the inverter electronics? That's a very good question. I don't know how to answer that question. It all depends on your experience. Like if I say from my experience that we did a bunch of demonstration projects last 10 years, most cases we did not see any major fault or like a failure in the inverter. On the other hand, one of the recent projects, last 6 or 9 months, again, the same example that we mentioned, the nighttime reactive burst support. We are frequently hearing from the system operator, again, we don't have any direct contact with the inverter vendor. Okay, this failed, this happened, we need to troubleshoot. So it might be one bad product or one bad installation or something may trigger that fault. But in general, I would say if it's a quality product, if it's gone through the standard testing, regression process, like some of the major manufacturer, then you can rely on that inverter. But still, there are a couple of other conditions you have to factor in. What is the environment where it's being installed? Same inverter might be installed in a very harsh environment without any proper maintenance, versus like exposed to the sun, direct sun, dust, blocking their air filter. So those kind of things will also factor in, because you have to understand this, especially the large inverters are exposed into the harsh environment, open to the sun, whole day, desert environment. So those will be also factored in, and typically manufacturers try to incorporate proper cooling system, because temperature is always the major issue. So if the cooling systems are properly designed and maintained, because I think those type of systems has a periodic maintenance requirement also, then you can rely to that. I would say again the same thing. The warranties are typically 5 to 10 years, may last even 15, 20 years with some parts replacement or some periodic maintenance. So if you ask me, I would say at this stage, PV inverters reach to a little bit of maturity compared to some other new technologies like energy storage, all still relatively new compared to PV. So you may experience more, maybe not catastrophic failure, but some troubleshoot needed for the energy storage. And it's also a complex system because you have battery coming from one vendor, inverter from another vendor, and someone else did the maybe system integration, then someone else put the energy management system. You can easily have 3 or 4 parties involved into an energy storage project. So that's another complexity. But hardware-wise, we have seen some good products from Germany, even China, that there are some good products we have seen tested. If you are looking for a direct statistics, those are very difficult to get those numbers because these are major system integrators keep them as a secret sauce, that how many tickets are issued. We did a study a couple of years back. Most of the cases failures are software related failure in the inverters. Like actual power stage failure is very rare event. Okay, so I don't see any other question. Just putting some reference, some simple white papers are available. The top 4 are actually published by NRECA, but available to EPRI members. EPRI also did a couple of white papers. Those are also available. Now, certification. The standard is 1547. It's just this requirement. It says how to test the product, but it does not provide any certification. That's why the UL comes into the picture. Many of you may be already familiar with UL 1741, which was the this thing was used for certification of inverters. So there are 3 types of terminology used to identify what type of certification it is. So that's why it's important to look for that when you look for a data sheet or the sticker on the side of the inverter, that what type of information is mentioned there. The first category is known as utility interactive, which is the traditional 1741, which was referring to the older standard like 2003 and .1 2005, basically disconnect immediately type of attitude. Then came the grid support utility interactive. So it's still utility interactive, but the grid support is being added. And this is on actually an appendix or supplemental requirement was developed a couple of years back and was developed first for the California Rule 21. If you guys are familiar with California did 3 phases of modification. Phase 1 was 2016 was approved. So once California approves that requirement, but there was no certification available. So that's why California UL developed this 1741 SA supplemental requirement or appendix SA, which defines tests which are kind of required to certify the California Phase 1 requirements. And the way you have to use the 1741 SA is that you always have to specify this test procedure will be applied against which requirement document, like source requirement document, commonly known as SRD. For example, 1741 SA plus California Rule 21. So now you know that this product is tested using the SA and the requirements came from Rule 21. Alternatively, it could be 1741 SA and then Hawaii Rule 14H. So that means same test procedure is used, but the pass-fail criteria is used from the California Rule 21. So that's the use of the SA. But SA did not have all the tests that you need to address 1547. That was the gap. Last 2 years, the industry realized and resolved it, that they found that SA, the way SA test procedures are defined, they're more like a California kind of a configuration. It did not have enough flexibility or also didn't have all the tests needed for the 1547. That's why this year, I think August 2020, so just a couple of months before, there was another supplemental was approved known as SB, UL 1741 SB, which is targeted 1547 2018 and .1 2020. So if you maybe next year, early next year, middle of next year, you want to use a 1547 2018 certified product in your project, most probably you should be asking for UL 1741 SB with 1547 2018 as the SRD document, or it will automatically mean that. And the sticker will say grid support utility interactive, will be the sticker. There is another category which is totally unknown. So for example, you want nighttime reactive power support and a vendor said, yes, I can provide that. Now, if you ask for a certification, right now there is no standard for that, most probably. So that will be a custom, like either utility or the vendor will provide a kind of a requirement document, like source requirement document, and then UL will certify the product against that requirement. It can come from manufacturer, it can come from the utility, whatever the agreement is, and then they'll have a special purpose utility interactive sticker there, or nomenclature there that this is a special purpose, and maybe it will specify which function or what it is. So these are the three mechanisms that UL has to certify products. Utility interactive is the old one, traditional one. Grid support utility interactive can cover California Rule 21, can cover 14H. SB will cover IEEE 2018. And then if anything that you want, those are not covered in those standards, will go into the special purpose category. Any question? Okay. If not, this is just a eye chart. The main thing we are trying to project when we can expect to see this 1547 compliant inverter will start coming into the market. And this is something that is regularly updated and saved in the IEEE website. So this link is there. You can go and check there if you want to know what's the current status. So I think the current expectation is that mid-2021 product certification most probably is going on right now, but early Q1, Q2, Q3 of 2021, you can expect to see products start coming into the market with the certification available. And many utilities, maybe many of you or your utility is also now getting ready in terms of modifying their interconnection requirement and make 1547 required to some form or fashion. So that's why it's important to know what's the status. I think some of the utilities already put January 2022 as a starting date for the requirement. Okay. This is the same thing just to highlight. Inverters with grid support capabilities, if you just say capabilities, many of those capabilities are already available. If you ask for certification, then Rule 21 and 14H kind of UL 1740 SS certifications are available. If you ask for 1547 2018 capability, available. Certification may not be, and not yet actually. Maybe within a couple of months or mid next year it will be, so not now. So that's the differentiation. Any question regarding a standard? I have just 2 more slides, then we'll be done. I'm seeing still already people are dropping. Okay, this is just to conclude the session. The reason DR is more challenging or DR interconnection is challenging, couple of reasons I can think of. Its size varies widely. It can be as small as even 1 kilowatt, or it can even be 20 megawatt express feeder connected to the substation, let alone the transmission. Transmission is a whole different story. Even for distribution, size can be easily 10 megawatt, 15 megawatt, 20 megawatt directly connected to the substation, or 5 megawatt with the load. Other part is a customer choice. A lot of cases, customer has wide variety of choices. It's not like your cap bank and regulators, only 2 or 3 brands. There are maybe 30, 40 brands of products available in the market. Location, it can be installed anywhere. There's a cheap land, maybe end of the feeder, thin wire, but land is cheap, so people will request a connection there. A lot of cases, interconnection requirements vary widely from one utility to another utility, one location to another location. So that's also very widely. And of course, the policy decision can accelerate or de-accelerate the penetration. A lot of cases, right now the trend is to accelerate the penetration. So even whether you're ready or not, you may see a lot of application and requests. Last slide, all these smart inverters are good. Those are very useful resources, kind of good tools to have in your toolbox. But that not necessarily that the silver bullet. You still need a lot of other factors, like T&D coordination is a major issue across the industry. That how do you coordinate the requirements, how do you do the co-simulation and all the service type of discussion. Open standards of protocols, at least to some extent, get maturity. Vendors are not opposing this adoption of one of the 3 standards. That's good sign. Still, the big question is control and communication. Definitely you have to do monitor, but you also may need to control and communicate with certain size of products. So what is the efficient and cost-effective way to do that? That has to be, a lot of research needs to be done there. Grid support, is it 1547 is giving you certain minimum capability available without any kind of discussion of who pays for it, but those are minimum capabilities. But if you want to use this enormous potential that smart inverters have, including nighttime reactive power support and other things, that has to go through some sort of incentivization mechanism. Who pays for it? Those kind of discussion. What is free because of the grid code like IEEE, or what has to be incentivized? If you guys are familiar, most probably many of you are the FARC order 2222 saying the DER can participate into bulk power system. So what is the mechanism for that? Authority. Most cases, those assets are not owned by the utility. So what kind of authority you have that you can use those resources? So some sort of agreement, part of your DR interconnection has to be there, that you can change power factor, you can activate certain functionality. So that has to be embedded in your contract, otherwise you don't have any authority. So those has to be part of the discussion and planned accordingly. So even if you are not using 1547 right now, maybe 2 years, you need to start the planning right now. So that's my last slide. Hopefully, you guys, still those who are on the call, find some information, useful information. And thanks for staying this late. One thing I request, if you don't mind, maybe spend 5 minutes to send me some feedback, like if you see something was good or something was not good, or anything that we can do to improve the quality of the, at least the online delivery of the tutorial, what can be done to improve it further. I'll greatly appreciate if you guys spend 5-10 minutes to send some feedback. Otherwise, thank you again. Have a great day, and hopefully we'll hear from you in a couple of our webinars that we are going to do next couple of weeks.